Welcome to this session on ad click prediction systems at Facebook. In this video, we'll explore how Facebook uses machine learning to predict whether a user will click on an ad, a critical component that drives the company's advertising business and user engagement. We'll break down the problem from end to end, starting with clarifying the business and technical requirements, framing it as a machine learning task, preparing the necessary data, and progressively improving our models, from logistic regression to deep learning and factorization machines. Finally, we'll cover how these models are evaluated and served in production, including pipelines for continual learning and real-time inference. By the end of this video, you'll have a solid understanding of how large-scale, production-grade recommendation systems are built and operated at scale. Let's dive in. The problem is to predict the probability of clicks on ads from a user. Here are some good questions to ask in the requirement clarification phase. Is the business objective to maximize revenue? What types of ads are there? Is continuous learning necessary here? Can we hide this ad or block this advertiser? Let's frame the ad click prediction problem from a machine learning standpoint. ML objective. The goal is to predict the probability that a user will click on an ad. This probability can be used to rank ads for a particular user in real time. Input. The input to our model is a user, represented via a set of features such as demographics, past behavior, click history, browsing behavior, session context, device, time of day, location. Alongside the user, we consider each candidate ad. Each ad is also described by its own set of features. Ad metadata, campaign category, text image embedding, advertiser info historical performance. Together, these form the user ad pair we feed into the model. Output. For each user ad pair, the model predicts a click probability. Ads are then ranked by their predicted probabilities. Highest ranked ads are shown first. Pointwise learning to rank, LTR. In this setup, we treat the task as a pointwise classification problem. Each example is a user ad pair labeled with whether or not the ad was clicked, 0 or 1. The model is trained to predict this binary label using standard loss functions like log loss, cross entropy. At inference time, we compute scores for all candidate ads for a user and sort them by score to form the ranked list. Advantages of pointwise LTR: simple to implement and easy to scale. Works well when we care about absolute click probability, not just relative order. Naturally fits into existing ad-serving infrastructure where probabilities drive downstream bidding, ranking, and budget allocation. This framing sets up the foundation for more advanced techniques later, such as pairwise or listwise LTR, multitask models, or combining CTR prediction with downstream metrics like conversion or revenue. In this slide, we walk through how we prepare the data for training an ad click prediction system, which is a critical step in ensuring model quality and performance. 1. Data engineering. We need to bring together data from multiple sources. Users. Each user is represented with a rich set of features, such as demographics, age, gender, location, behavior history, pages liked, past ad interactions, browsing activity, device and session context, ads, metadata, e.g., ad type, text, image, category, campaign goal. Historical performance data, click-through rate, conversion rate. Interactions, clicks, impressions, hides, conversions, and skips. This is our label data, 1 for a click, 0 for no click. These are typically stored in high-volume logs and require aggregation, deduplication, and joining across entities. 2. Feature engineering. Once raw data is collected, we need to extract and transform it into useful features. A. User features, static, demographics, dynamic, recent click patterns, engagement scores, session time of day, embeddings, learned user representations from past behavior. B. Ad features. Textual content can be encoded using transformers like BERT images. Use visual embeddings from CNN's campaign info, advertiser ID, bid price, ad category, C. Contextual features device type, mobile, web, location timestamp, hour day of week, ad position on page D. Interaction. history number of recent impressions, clicks, hides, click-through rates per category or advertiser recency and frequency metrics. 3. Dealing with class imbalance. Since our relatively rare events compared to impressions, we face a heavily imbalanced dataset. Strategies to handle this include undersampling of the majority class, non-clicks, class-weighted loss functions, focal loss to focus training on harder examples. 4. Label construction and logging delays. The label, click, yeah, no click, may depend on delayed feedback, like post-view conversions. We need to ensure alignment of feature snapshot and label timestamp. We also create negative samples from impressions that didn't result in clicks. 5. Final dataset construction. The final training dataset consists of input, user features, ad features, context. Output, click label, 0 or 1. Data is usually stored as TF records or Parquet for scalable training and is often updated on a daily, hourly cadence for freshness. This pipeline feeds into model training, and the quality of this preparation step directly affects predictive accuracy and downstream performance. In this section, we're going to look at how we can use logistic regression for the task of predicting ad clicks. Logistic regression is a widely used baseline model for binary classification problems like this one, where we want to predict whether a user will click on an ad or not. There are a few reasons why it's often used in industry. It's fast to train and easy to implement, which is important when you're working with large-scale data like Facebook's ad impressions. Potentially, billions of records per day. It's interpretable. You can easily examine feature weights and understand which features are most influential in driving ad clicks. However, logistic regression also has some important limitations. First, it doesn't handle nonlinear relationships well. It assumes a linear relationship between the input features and the log odds of the click. Second, it's not effective at capturing complex feature interactions. For example, the interaction between a user's location and the time of day might be very predictive of ad engagement, but logistic regression won't model this automatically. To work around this, we often apply feature engineering techniques like feature crossing. Feature crossing creates new features by combining existing ones, for instance, multiplying or concatenating them, to help the model capture nonlinear effects. For example, we might create a new feature like device.type X ads category, which could highlight that users on mobile devices engage more with ads for local restaurants than users on desktop. While logistic regression can be a good starting point, in practice, we often combine it with richer models that can better capture nonlinearities and interactions, such as deep learning models or tree-based ensembles. Let's now examine the role of gradient-boosted decision trees, or GBDT, and how they can be combined with logistic regression in ad-click prediction systems. Gradient-boosted decision trees, GBDT. GBDTs are one of the most widely used algorithms in industry for tabular data, and they often yield state-of-the-art performance for tasks like click-through rate, CTR prediction. They work by iteratively training a sequence of decision trees, where each new tree learns to correct the errors made by the previous ones. This makes them very effective at capturing nonlinear patterns and high-order feature interactions. However, there are some limitations. GBDTs are inefficient for continual learning. Unlike neural networks, you can't just fine-tune a model with new data. You typically need to retrain from scratch. They cannot learn embeddings from high cardinality categorical features, such as user IDs, ad IDs, or page types, which are prevalent in ad systems. GBDT plus logistic regression, two-stage model. To address some of these limitations, a common hybrid strategy is to combine GBDT with logistic regression. Here's how it works. First, we train a GBDT model to learn complex patterns from the data. Then, we use the output of the GBDT model, either the leaf indices or high-gain splits, as new categorical features. Finally, we feed these features, along with original inputs, into a logistic regression model to make the final prediction. This approach leverages the strength of GBDT in feature transformation and the strength of logistic regression in efficient serving and online updates. But there are still drawbacks. This model still struggles with complex interactions between sparse or high-dimensional features, especially when embeddings would be more appropriate. Also, it's not ideal for fast continual learning, since GBDTs are static and hard to incrementally update. Summary. While GBDT and GBDT plus LR are very strong baselines in CTR prediction, they have clear scalability and flexibility limits compared to deep learning approaches. That's why many modern systems move toward neural network-based architectures when dealing with large-scale, high-dimensional, and rapidly evolving data. Now let's explore two powerful neural network architectures commonly used in modern ad-click prediction systems: the two-tower architecture and the deep and cross network, DCN. Two-tower architecture. This architecture separates the modeling of the user and the ad into two distinct neural networks, or towers. The user tower takes in user-specific features like demographics, historical activity, and device type, and maps them into a dense user embedding. The ad tower encodes ad-related features, such as ad ID, campaign type, content category, and creative style, into a dense ad embedding. These two embeddings are then compared, often using a dot product or cosine similarity, to estimate the relevance score between the user and the ad. Why use this? It's efficient at serving time since ad embeddings can be pre-computed. It generalizes well to new user-ad combinations. It's also well suited for nearest neighbor retrieval during candidate generation. Deep and cross network, DCN. The DCN architecture addresses two important modeling goals: generalization, using a deep neural network that captures complex, high-order, nonlinear feature interactions. Feature crossing, using a cross-network that explicitly learns useful combinations of features, like young users plus gaming ads, without manual feature engineering. The architecture works by running raw features, dense plus embedded sparse features, through both the deep network and the cross-network in parallel. The deep network focuses on general-purpose representation learning. The cross-network explicitly models interactions between raw features across layers. Finally, the outputs of both networks are concatenated and passed to a prediction head, usually a fully connected layer followed by a sigmoid, to predict the click probability. You can also combine both approaches. Use two-tower for generating top-N ads, and a DCN or similar architecture to re-rank the shortlist. Let's now talk about embedding-based models, a powerful class of models that improve over traditional methods like logistic regression by effectively capturing feature interactions. Embedding-based models and factorization machines. The core idea here is to assign each feature, whether categorical or numerical, an embedding vector. Then, instead of using raw feature combinations, we compute the dot product between embedding vectors of each pair of features. This dot product represents their interaction strength. This is the foundation of factorization machines, or FMs. FMs. Capture all pairwise feature interactions automatically. Avoid the need for manual feature crossing. Work well with sparse, high-dimensional inputs, which is common in ad systems. Think user IDs, ad IDs, device types, etc. So instead of trying to build explicit rules for things like young users click mobile gaming ads more on weekends, the model learns these interactions directly from the data. Deep FM. Combining strengths of FM and deep learning. Deep FM takes this one step further by combining a deep neural network, DNN, with a factorization machine in a single architecture. The FM component captures low-order, pairwise feature interactions efficiently. The DNN component captures high-order, nonlinear feature interactions that the FM alone would miss. The final prediction is made by combining the outputs of both branches. This hybrid approach gives you the best of both worlds: strong generalization from the DNN and fine-grained pairwise modeling from the FM. Extensions: Deep FM plus GBDT. You can even extend this further by combining GBDT for feature selection or pre-processing, and then feeding the selected features into a Deep FM model. This helps with feature reduction and selection from noisy inputs, better generalization in sparse or imbalanced data. Overall, embedding-based models, especially Deep FM, strike a good balance between predictive power and flexibility, making them highly effective for ad click prediction at scale. To ensure our ad click prediction system performs effectively, we need to evaluate it using both offline and online metrics. Offline metrics. These help us gauge model quality before deployment. Cross-entropy loss. This is our primary training objective. It measures how close our predicted probabilities are to the true labels, clicked or not clicked. Lower values mean better calibrated predictions. Normalized cross-entropy. This provides a baseline comparison by normalizing cross-entropy with respect to the entropy of the actual click rate. It tells us how much better our model is compared to a naive guess, like always predicting the average CTR. A value closer to 1 indicates a well-performing model. These offline metrics are critical for model selection and tuning during development. Online metrics after deployment, we track how well the model performs in the real world through online A/B tests, click-through rate, CTR, the most basic metric, percentage of ad impressions that led to a click. While easy to track, it doesn't tell the whole story. Conversion rate. This measures what happens after the click. Did the user complete a meaningful action like a purchase or sign up? It reflects the actual value of the click. Revenue lift. At the end of the day, the business impact matters. Revenue lift measures the increase in revenue due to the model, accounting for ad monetization effectiveness. Hide rate. A quality signal. How often users hide or report ads is irrelevant. A low hide rate suggests the ads are well targeted and not annoying. Offline metrics help us iterate quickly, but online metrics are the ultimate arbiter of success. They tell us whether our models drive user engagement and business impact in a real-world setting. It's important to monitor both continuously. Let's walk through the end-to-end system pipelines that power ad click prediction at Facebook, from data generation to model serving and continual improvement. Data preparation pipeline. The first step is feature computation. We compute both. Batch features, such as historical engagement stats, on a daily basis. Online features like real-time user behavior or recent ad impressions, updated in near real time. We continuously generate labeled training data from user ad interactions. For example, if a user sees an ad and clicks on it, that interaction becomes a positive training sample. This pipeline ensures that our models are always trained on fresh, high-quality data, capturing the constantly evolving user and ad landscape. Continual learning pipeline. Instead of retraining from scratch, we often fine-tune existing models using recent data. This is much more efficient and helps the model adapt to shifting patterns quickly, like trending topics or new advertisers. Each new version of the model is evaluated rigorously using offline metrics and possibly small-scale online tests, A/B tests. If the new model outperforms the previous one, we automatically deploy it to production. This process allows us to support continuous improvement while minimizing risks to user experience or advertiser outcomes. Prediction pipeline. Serving. This is the real-time system that delivers ads to users as they browse. It takes a user request containing user info, context, and session metadata, and performs 3 key stages. 1. Candidate generation. The system starts by narrowing down billions of eligible ads to a manageable few thousand using lightweight retrieval techniques, e.g., rule-based filtering, basic matching, or embedding similarity. 2. Ranking model. These candidate ads are passed to a deep learning model that estimates the click probability for each user ad pair. This stage is latency sensitive and highly optimized. 3. Re-ranking service. Finally, we apply business constraints and logic, such as ad diversity, budget pacing, or policy filters. This re-ranking ensures that we balance user satisfaction, advertiser goals, and platform integrity. To summarize, data pipelines generate high-quality training samples. Continual learning keeps models fresh and relevant. Prediction pipelines serve optimized ad experiences at scale and speed. These pipelines work in tandem to create a seamless and effective ad recommendation engine that can react quickly to new data, deliver relevant content, and optimize for performance in real time.